All right, let's dive in. We're going to crack the code of the invisible world around us. Seriously, we're going to understand the fundamental changes that are happening all around us and even inside of us every single second of the day.
Think about it for a second. Milk sours if you leave it out. An iron pan gets all rusty if it gets wet. You throw a bunch of ingredients into an oven and somehow it becomes a meal. Now these things seem totally different, right? But they're actually all just pieces of the same giant puzzle. They're clues. So, what's the big secret?
Every single one of these things, from that sour milk to grapes turning into wine to the very breath you're exhaling right now, is going through a massive transformation. And here's the secret. They are all chemical reactions. It's just chemistry in action, taking one thing and turning it into something totally new.
Okay, so if we're going to understand all this, we need to start thinking like detectives. And our very first step, it's learning how to spot the evidence. The telltale signs that a chemical crime has even happened in the first place.
It's a really good question, isn't it? We can't exactly see the tiny atoms rearranging themselves. So what clues do they leave behind for us? What are the fingerprints of a chemical reaction?
And here they are. These are the 4 big ones our chemical detectives are always on the lookout for. Did a liquid suddenly turn into a solid? Did something clear suddenly turn bright green? Are there bubbles showing up out of nowhere? Or did the beaker suddenly get super hot or maybe even icy cold? If you spot any of these, you can be pretty sure you're watching a chemical reaction go down.
Okay, detective, we've found the evidence. Now what? Well, every good detective has to write up a report. And scientists do this using a special, universal language that's designed to describe exactly what went down. We're talking about the language of chemical equations.
The simplest place to start is just a word equation. It's basically a sentence. It clearly tells you the reactants, that's the stuff you start with, and the products, that's the new stuff you end up with. So here, magnesium and oxygen react to become magnesium oxide. Nice and simple.
But scientists love being efficient, so they use chemical symbols to make what's called a skeletal equation. It's the shorthand version. Mg plus O2 gives you MgO. It's short, it's sweet, but there's a problem hiding here. This simple version, well, it isn't telling us the whole story.
Yeah, look closer. On the left side, the reactant side, we're starting with 2 atoms of oxygen, that O2 molecule. But then look on the right, the product side. We've only got 1 oxygen atom in MgO. So, where'd the other one go? Did it just poof? Vanish?
No way. It can't just vanish. And this brings us to the absolute golden rule of chemistry. This is a fundamental law of the universe, the law of conservation of mass. You can't just create atoms out of thin air, and you definitely can't make them disappear. Whatever you start with, you have to end with.
So, to follow the law, we have to balance our equation. Think of it like balancing your bank account. What goes in must come out. This here shows the step-by-step for a reaction between iron and steam. Now, the trick is, you can only add big numbers, called coefficients, in front of the molecules. A good strategy is to start with whatever looks most complicated. In this case, the Fe3O4. When we fix the oxygen atoms first, it kind of sets off a chain reaction that tells us how to fix the hydrogen, and then finally the iron. It's like a little logic puzzle.
And there it is, our finished report, the perfectly balanced equation. Now, if you go and count all the atoms, you'll see there's the exact same number of iron, hydrogen, and oxygen atoms on both sides of that arrow. The books are balanced. This is the true story of what happened.
Awesome. Now that we can read and write the language of chemistry, let's check out some of the most common plots. These are 4 classic types of reactions you're going to see again and again. You can think of them as the main genres of the chemical world. So first up, we've got 2 types that are literally perfect opposites. On one side, you've got a combination reaction. That's when 2 or more simple things team up to form one more complex thing. A and B get together to make AB. And the exact opposite of that is a decomposition reaction, where one big thing breaks apart into simpler pieces. AB splits up into A and B. One builds up, the other breaks down. Simple as that.
Okay, let's move on to the next type. And for this one, let's picture a little scene from the lab. We take a regular old iron nail and we dip it into this really beautiful bright blue liquid, a solution of copper sulfate. Now here is the key thing to know. In the world of elements, some are just more reactive, more aggressive, you could say. And it just so happens that iron is more reactive than copper. So, when this more assertive iron meets the copper that's already chilling in a compound, what do you think is going to happen?
The iron literally kicks the copper out of its spot. It just displaces it. The iron jumps into the solution to take copper's place, and the copper gets forced out as a solid metal, which is why the nail gets that brownish coating. And that bright blue color, that was from the copper sulfate. Since that's gone now, the solution fades. It's a total chemical power play.
So our last reaction was one element kicking another one out. But what happens when two compounds meet? Well, in a double displacement reaction, it's like they all swap partners. The sodium decides to hang out with the chloride, and the barium pairs up with the sulfate. And in this particular dance, the new barium sulfate pair is what we call an insoluble solid. It doesn't stay dissolved, so it falls out of the solution as a cloudy substance called a precipitate.
Okay, we've cracked the code. We've learned the classic plots. For our final act, let's bring our detective skills all the way back to where we started and solve some real-world mysteries. We're going to focus on one of the most common reactions out there, oxidation. Hey, remember that rusty iron pan from the beginning? Well, rusting is just the common name for corrosion, and corrosion is just a slow oxidation reaction. The iron is reacting with oxygen and water in the air. And it's the exact same thing that happens when your silver jewelry gets that black tarnish or when copper gets that greenish coating. It's the metal slowly being attacked and changed by its environment.
And this whole process isn't just for metals. Have you ever smelled cooking oil that's gone bad? Or tasted crackers that are just stale and off? That awful change in taste and smell has a name, rancidity, and it's the exact same process. The fats and oils in the food have oxidized by reacting with oxygen in the air.
Which finally solves a classic mystery. Why are chip bags always half full of air? Well, guess what? It's not air. To stop the oils in the chips from oxidizing and going rancid, the factory flushes the bags with nitrogen gas. The nitrogen pushes out all the oxygen, which basically stops oxidation cold and keeps those chips crispy and fresh. It's a pretty brilliant bit of everyday chemistry.
And all this brings us to a really important point, and this quote just says it perfectly. You know, memorizing that iron plus oxygen makes rust, that's just a fact. It's like one word in a dictionary. But understanding why that happens, the process of oxidation, and then realizing that same process is what makes your chips go stale, that is science. It's about connecting the dots to understand the story of how the world really works.
So let's end with this thought. The very energy your brain is using to understand my voice right now is coming from a chemical reaction happening in your cells called respiration. It's a type of oxidation, and it's releasing energy, which makes it exothermic. You are literally powered by chemistry. So the real question is, what other hidden chemical reactions are shaping your world right now? The cool part is, now you have the tools to start finding out.